Hey, welcome back to Fan Mama Physics. In this video, we are going to go over an example using conservation of momentum and a dab of energy in there. Haha. So I do example 5, you do example 6, which is below here. So let's get started. In the diagram below, we have a ballistic pendulum system. We have a bullet, that's the mass of our bullet, I'm going to label that. It is fired at some speed at a wooden block, and I'll just write that as initial for the bullet. Initial speed for the bullet velocity. At a wooden block, this I'll just write MW for wooden block, tied to by massless ropes to ceiling, not going to affect our system. After the bullet strikes the wooden block, it comes to a stop and is embedded inside the block. Actually, that's not correct. It's embedded in the rock. Because it's still moving with the wooden block, so it can't just come to a stop. It's a stop relative to the wooden block. Okay, I digress. During this time, the wooden block swings upward and achieves a certain height, like we saw in the video. As either in the diagram, we want to calculate the height that is achieved by the wooden block. So many times when I have students that would do this problem, they make this key mistake, and they think, ooh, hey, I have a bullet that has a lot of kinetic energy. It's going to transfer all of that energy into this one block, and together they will go up to a certain height, therefore converting all of that to potential energy. Ouch. That's a mistake to think that, because why? First of all, when the bullet enters this block, it's going to a lot of that energy is going to be lost in the form of thermal energy, because you might have the bullet rubbing against the insides of the block, where there's a lot of friction energy involved, and it might compress the block, and there's sound energy involved. There's so much energy that's being lost from this system that we cannot trace. Because the system loses that energy, not all of the kinetic energy will be converted to potential energy at the end. So conservation of energy is not going to work here, because there's joules of energy that we can't trace where it is going. What we can do is we can find the part where this block, as the bullet is now embedded inside, after it's embedded inside, notice from the video, it started to move with a certain speed going up to the top. Okay, so after the bullet collides with the block, that part, it's a clean energy conversion from kinetic to potential, which there's not going to be a lot of energy lost due to friction or other forms. It's just a pendulum as it's moving up now. But before the pendulum, before it starts moving up, there's that collision. And that collision, there's so much energy, so much untrackable energy. We might as well use some other tool to help us figure out what's happening then. So that point in time, we can use conservation of momentum instead. So that's kind of like me breaking this problem in half, where the second part we're going to deal with just the bullet block traveling up together. The first part, we have this collision here. So when we have this collision, why can we use conservation of momentum? Well, key thing is it's easy. It's stuff that we know we can use. Why? Because when the bullet interacts with this block here, all the forces that act on one another, they are internal forces. If there are internal forces, then that means the total momentum of our system stays the same, meaning the bullet block system. Going back to conservation of momentum, when our system is isolated, there is no net external force, the total momentum in our system should be the same. So these internal forces, the friction force acting on each other, blah, 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 we don't care about that. We can just ignore it when we deal with conservation of momentum. The total momentum of my bullet before the collision and the total momentum of my bullet block going off together after the collision, that's going to be the same before and after. So that's why it's easier to look at conservation momentum. We can just ignore all those friction forces and energy that's being lost. We can ignore that and just look at the total momentum in our system. So so now we have a two-part system. We're going to deal with conservation of momentum here, and we're going to deal with conservation of energy there. Okay, so now we can actually get down to work. For momentum, we have the bullet here with some initial speed. That's the initial part. So I'm just going to write MBUB. The block wasn't moving to begin with. So that's our total momentum before the collision. After the collision, our mass of the block and the wooden block are now together, and they're going to leave with some final velocity, which we don't know. So then the first step is to solve for this final velocity that they leave off with. And once we know that final velocity, we know the kinetic energy of the block bullet system before it gets converted to potential. So that's the workflow now. Now we can actually get down to business. We are going to solve for this final velocity by dividing both sides by the combined masses here, and then putting in all our values, then we can solve for the velocity. When we put in the mass of the bullet, don't forget that it's in grams. So to convert it to kilograms, we need to divide this by 1,000. Therefore, 3 decimal places, 1, 2, 3, giving us 0.052 kilograms. Okay, so that's what we need to put in. The mass of our wooden block is 0.77 kilograms. So 0.052 kilograms times the speed of velocity, which is 290 meters per second. And the bottom we have the mass of our bullet plus the mass of our wooden block, and putting all of that into our calculator, we get 18.345, which then we're going to need to save all those digits, 345, because we're going to need that velocity in our second part, which then all this kinetic energy is going to be converted to potential. There is no potential energy to start off with because the block starts off, say, at height of 0. That's our reference point. And at the end, when it reaches our final height, there is no kinetic energy final because the block comes to a momentarily stop. So it's just EK initial equals EP final. And then we know kinetic energy is 1/2 mv squared. That's equal to mgh final. And hey, the masses cancel. That is always good to know. And we're just solving for the h, so we're going to divide both sides by g, which then we get h final is equal to 1/2 v squared over g. And that v is just this velocity that we have here. Gravity is 9.81, and then putting everything in, we get 17.15. Oof, that is a very large, and that's going to round to 17 meters. Yeah, that's a little bit unreasonable. I think I gave the bullet too fast of a speed to begin with, so anyway, so this is how you would tackle a problem. So first of all, we had a collision of a bullet with a wooden block, and since we can't track all where the energy goes, it is much easier to use conservation momentum where there are no net external forces acting on our block bullet system during that collision. And after the collision, we can then use conservation of energy to find out how high it goes after we know the velocity of the wooden block bullet system as it starts to make its way up, okay? So I have a very similar problem for you to try. And this time we're talking about carts traveling on a path. They're going to go up this hill here. We get to ignore friction, and you're just trying to find the height. Good time to pause the video, and I will do the solutions here on now Fast Play. Okay, we have the same mass for both the carts, in which the second one is at rest and 0.25 kilograms. So let's deal with the collision first, before and after. Before the collision, the first mass was moving at 3 meters per second. The second mass of the cart is not moving. So before the collision is just m times u. After the collision is the two masses combined times their velocity leaving. That's the same as 2m, and the masses cancel out on both sides. Then I can divide both sides by 2 to give me initial velocity of the first cart divided by 2 equals 1.5 meters per second. The second part, in which they leave and go up the hill, that's the kinetic energy converted to potential energy. So then masses cancel out in that equation, and putting into the velocity that we got in the collision part inside, we get 0.11 meters. Okay, here we have the solutions to the problem, very similar to the last case, but now because we have the two masses being the same, I just use m for my variable here. So I have mu for the mass of the cart times its velocity in the beginning, the second cart wasn't moving, equal to the total momentum afterwards, which is just two cars combined times some final velocity there. So these two m's as I add together gives me 2m. And then as a result, hey, the m's can cancel out on both sides of my equation, and I can then just move 2 to the other side. I get v is equal to u over 2, then giving me 1.5 meters per second. And the other parts of the step are very similar to that of above. We get a total of 0.11 meters. So there are your solutions. Hopefully you learned something in these examples that you can apply yourself. Thank you for watching. Good luck. Fat Mama Physics signing out.